Hi, welcome to lesson 4.4, Rates of Change in Polynomial Functions. The goal for today's lesson is to determine average and instantaneous rates of change in polynomial functions. And the reason for doing this is so that we will become proficient and efficient at using a variety of different polynomial functions using the difference quotient and the average rate of change formula. Okay, so let's recall that the average rate of change of a function is and I will pause briefly to ask you to fill this in. The average rate of change of a function is sorry about my writing, slope of the secant between 2 points. And the average rate of change, the formula for this then, is f of x2, or y2, minus f of x1, or y1, all over x2 minus x1. So this is really nothing more than the slope formula, y2 minus y1 divided by x2 minus x1. Let's now recall that the estimate of the instantaneous rate of change of a function is the average of the slopes of the secants between 2 points that are very close together. One secant preceding and one secant following a given value of x, referred to as a. That's just the name that we give that specific value of x. Where we're focusing on to find the slopes of the secants preceding and following. Therefore, the average rate of change is f of a plus h minus f of a all over a plus h minus a. And in this way, as we've done in the past, we see that the a's cancel each other out. So we're just left with f of a plus h minus f of a all over h, where a is some specific value of x, and h is a small number like positive or negative 0.001. Recall that h is just that tiny, tiny horizontal distance between two x values. And the x values are the independent values, thus determining the function values, the f of x values, which are the dependent values. Thus, the estimate we know that it's always the estimate for now until we get into calculus. The estimate of the instantaneous rate of change is the average of the calculations of the slopes, I guess, of the secant. If I can squeeze this in, secants between the 2 points a plus h, f of a plus h, and a f of a, where h is assigned both values of 0.001 and negative 0.001 for the two calculations of slope, thus resulting in two values with which to take the average. All right, so let's take a look at how this will all work once we start using polynomial functions. So what I'd like you to do is pause the video and determine the average rate of change for each of these intervals that are listed here in part A, 1, 2, and 3. And then come back and take a look at the solutions that I provide here just to see if they match. The one other thing to look at here is, let's not forget about all the things we've done with functions in past years. Take a look at this to see what kind of function it is, where any features that you might recognize would be located, and then get a mental picture or even sketch a little graph of this function so that you have an idea of what's actually transpiring here. Okay, so please pause the video now, and we'll come back in a second to verify what you've done. So if we take a look at this function, we see that the a value, the vertical stretch, is 3. So it's vertical stretch by a scale factor of 3. It's in vertex form. This is a quadratic because of the degree 2. And so the vertex is at the coordinates 2, negative 2. Okay, so just so we have a little general idea, general look at this. So it's at 2, negative 2. So it's going to be something like this. I don't know exactly where the zeros are, but at least so we have a bit of an idea of what's happening with this parabola. Okay. So we want to determine the average rate of change of f of x on the interval from 2 to 4. So the average rate of change, and I might get lazy here in a second and just write m, because we know that the average rate of change is the same as slope. But the average rate of change is f of x2 minus f of x1 all over x2 minus x1. And so f of x2, well, I'll use 4 as x2. So here I'll do the 4 minus 2 on the bottom. And then f of x2, 4 goes in here. 4 minus 2 is 2. 2 squared is 4 times 3 is 12 minus 2 is 10. Minus, and then substitute 2 in here. 2 minus 2 is 0 squared times 3, negative 2. And then we just work this out. So 10, that's 12 over 2, which gives me an average rate of 6. All right, so now let's do the same thing over here. So the average rate of change, again, same formulas over here, so I won't repeat it just for the sake of brevity. F of x2, so x2 is going to be my 6. 6 minus 2 is 4. 4 squared is 16. 16 times 3 is 48. 48 minus 2 is 46. And then substitute in 2 again. Same sort of result as what we had before, so that's negative 2. And then we divide by 6 minus 2. So we get 48, because it's 46 minus negative 2, which is 48, divided by 4, which is 12. So the average rate of change between the 2 points, between x values of 2 and 4, is 6. The average rate of change between the 2 points where the x values are 2 and 6 is 12. And now the average rate of change here on the interval from 4 to 6 is, we've got the 4 is 10, the 6 is 46. So we do 46 minus 10 all over 6 minus 4. So we get 36 divided by 2, which is 18. Okay, so notice, take a little look here. See if this is worthwhile doing. Take a look at the rates of change here over the three intervals. So from 2 to 4, the average rate of change is 6. Now notice that 2 is, x equals 2, is right at the vertex. Okay, so that's 2. And then 4 is a little bit to the right. So that average rate of change is 6. If I were more proficient at this program, I would draw a line in there. And then from 2 to 6 in that interval, 6 is further to the right. And you can sort of imagine that the line would be steeper, and thus we can tell that it's the slope is 12. And then when we go to this third interval, when x is between 4 and 6, we see that 4 is starting over here and 6 is further yet, or not further yet, but we're going from 4 to 6, and it would look like it would be steeper if we could imagine a set of secants passing through that parabola at different points. Okay, so that kind of makes sense. All right, let's check out the next page.